It's all joined with my advisor, Mahan Maharaj. So, before I get down to serious business, there's a very quick review of CAD0 cube complexes. Just, for those who haven't seen it too many times. So what is an n cube? It is an n times product of the interval. Here is a lazy 2 cube. And a subcube is like a face of my n cube. So my 2 cube will have two kinds of subcubes. This is one subcube and this is 0 subcube. And a cube complex is a collection of cells, collection of n cubes for varying n, glued isometrically along subcubes. And here, when I use the word isometrically, you can, well, you have some leeway in choosing the metric, but let's say you have the L1 metric. Okay, so this is also a very quick drawing of a cube complex. Okay, and when is a cube complex CAD0? The two conditions, the first one is that every link is flag simplicial complex. So links are little epsilon balls around vertices of my cube, vertices of my cube complex. And what is a flag simplicial complex? Very quickly, it is every n plus 1 tuple in, let's call this x, x is my cube complex, in x spans, okay, not x, actually in the link, I don't want to say x, sorry, spans an n cell if and only if they are pairwise adjacent. Okay? Or in other words, you have the n cell if and only if you have its one skeleton. And number two is that it should be simply connected. And this cube complex I've drawn here, it is actually a CAD0 cube complex. And here is what are cubulable groups or cubulated groups. You say a group is cubulable or cubulated if it acts geometrically and via, well, isometries in this setup, cubical isometries. So this is a CAD0 cube complex. So it acts geometrically and by cubical isometries, then we call it G is cubulable. Or we also use the word cubulated simultaneously. Okay, and well, what are a few properties of a group being cubulable? Well, we have seen way too many of them last week, and there are even more which haven't seen last week. But yeah, just to recall a few. So a cubulable group is biautomatic. A cubulable group has a very strong negation of property T, and a cubulable group, if it's also hyperbolic, then is hyperbolic, and if it has the first L2 Betty number to be 0, then it virtually algebraically fibers. So these are two things that we've seen last week. I'm not writing down any more. And here are a few examples. Again, there are lots of examples. I'll just write down the ones which are relevant for our talk. So case number 1 is due to a lot of people. It's a very famous work. Kahn-Markovich and Bergeron-Weiss. But this work was also done by Dufour. So this is fundamental group of any closed hyperbolic 3-manifold. And an easier example, much easier example of this is fundamental group of closed surfaces, but yeah, you can actually take it as an exercise if you haven't done this before. This is example 1. And example 2, the class of example is due to Weiss, which is that if you have a group which is a hyperbolic splits as a graph of groups with quasi-convex edge groups, which means that the edge 2, the whole group embedding, these are quasi-convex. And number 3 is that all the vertex groups are cubulable. If all these scenarios hold, then my final group G is also cubulable. So this is an easy part of Weiss's quasi-convex virtual hierarchy theorem. Okay, so the point that I want to note down here is that this is really a quasi-convex combination theorem for cubulability. Okay, so it's a combination theorem because you start with some cubulable groups and put them in a graph of groups, and then you get another cubulable group. And it's a quasi-convex combination theorem because the edge groups are quasi-convex in the whole group. So what the context of our work explores is the non-quasi-convex case. Question. And the answer to this question is broadly unknown. There are, well, some known examples, and I'll start with one of them. So this comes from extensions of surface groups by free groups. So there's a surface group, there's a free group, and suppose that G is hyperbolic. And the question is G cubulable? So point number 1 is this surface group is a normal subgroup in a hyperbolic group, so it can never be quasi-convex. It's non-quasi convex. And point number 2 is when n is equal to 1, you have z over here and a surface semi-direct with a z subgroup z. So that is exactly the case of a fibered 3 manifold, and which is hyperbolic. So that is cubulable by all this work over here. So the n equals 1 case is done. Now, before I write the n equals 2 case, I want to say why I brought this up in the context of combination theorems. So let's just quickly draw a space for the n equals 2 case. So I'll draw my little graph over here with 2 loops. So it has fundamental group F2, and above it I have my surface bundle. So this is my bundle E over the graph G. Okay, so is the picture visible over there? Okay, somewhat. Another question is hyperbolicity of, hyperbolicity. Cubulability of pi1e is the same as this combination theorem. Combination theorem, well, I'm just writing down 2 statements. So if I have this 3 manifold M1 here, and I write the 3 manifold M2 over there, then pi1e is nothing but pi1 of M1 star pi1 of M2 over the surface group. And so the group on the left is cubulable. It's a fibered hyperbolic 3 manifold. Same for the right. The group in the middle, this is non-quasi-convex because it comes from an exact sequence like this. So this would be an example of a non-quasi-convex combination theorem. So that is why, well, bundles, surface bundles over graphs come in. Okay, and I'll just quickly say that there are very few known results. If you want to say a question is, there are some results due to Maharaj, Manning, and Sagiv to say that positive examples exist. But general cases are known. And so this is the backdrop of our work. This is where our theorem starts to take place. So, are there any questions? Okay. So the thing is, trying to cubulate this entire bundle over this non-quasi-convex subgroup is like a bit too hard, I guess. And you don't really have any control over the quasi-convex subgroup. So the idea here is to break the non-quasi-convexity in some way. So here comes this process of drilling. So So let's explain what it is. And before I proceed, I'll just draw a huge picture on what I do on that side, just to make my life easier. Okay. So again, recall that we have this bundle over graph G with some surface, genus G greater than or equal to 2 fibers. Do as follows: to pick a collection of points, it's a finite collection, so 1 to n, from your graph, minus the vertex set of the graph. You don't pick any vertices. So for example, here I can just pick my x0 over here, and let's say x1 over here. And now you also pick a collection of essential simple closed curves from your fibers over the points that you just chose. Okay, so I have a fiber over here. And from here, I choose one curve. And I also have a fiber, so I'm just drawing, hanging somewhere inside the 3 manifold. And I choose another curve over here. Call this sigma 0, and call this sigma 1. Now the point is, there are no restrictions on the choice of base points that I've made here. So they are not the vertices, but they can coincide. So I could have x1 equals x2 over here, even though I have not taken the case. So when they coincide, I need to put an extra assumption that the curves that I've chosen, they are disjoint. Okay, that's condition number 1. And, well, actually, that's good enough for now. And now that I've chosen these curves, we do this drilling operation, which is we take the original bundle and throw away small tubular neighborhoods of my simple closed curves. Okay, so what does that look like here? So tubular neighborhood of a curve is a solid torus. So throwing it out would make sure that I have a torus-shaped hole inside my picture. This is a very schematic picture, so you're free to not believe it. And I have better working examples, working pictures, but it'll take too much time to draw them. So this is one torus I've removed, and here is another torus I've removed. Okay, so is someone visible? I hope it's visible right over here. But right, so this is my drilled bundle. I call this a drilled bundle. And so is the construction clear? Okay. where do I start? Huh? Yes. Yes, I picked points from interiors of edges, and I picked looked at the fibers and took essential simple closed curves from the fibers, and well, I made sure that these curves are actually disjoint, and then took tubular neighborhoods of these essential simple closed curves and threw them away from my original bundle. So, okay. Such a thing as in the remainder of the bundle. So the neighborhood of these curves will be solid to right. Yeah, so I'm just showing my solid to right, and what you'll see here, what I've drawn over here in orange, these are the boundary solid to right. Okay. Exactly, epsilon is small enough so that neighborhood of disjoint from each other. Neighborhoods are also disjoint from these special fibers that I have over the vertices, and like, yeah. So it'll be clear how many how many drillings you have to be doing. Okay. Not necessarily. Like for a result, one per edge would be like definitely enough, but don't need to. So let's see. So here's the theorem that we've proved, which is that the drilled bundle group is cubulable if some pretty straightforward conditions hold. One is that we start with a hyperbolic group. Two is that no sigma I and sigma j are homotopic inside P for all ij. And number three is a bit more wordy. So says that restrict E to each component of the complement of the drilled points. So this is all xi, looking at the complement of all xi. Then each such restriction has cubulated fundamental groups. Okay, so does this third thing make sense? You're restricting your bundle to so what is before drilling? The third point is, yes, before drilling, if you restrict the bundle to all the complements of your drilled points. Yes, yes. If you have these two cases, then you're safe. There could be more cases, well, I've not listed down. Yeah. Okay, for example, if the complements come from the example set, these three have already solved, then also we are good to go. Okay, yeah, so it's too bad. So each component of the complement of the graph, so graph minus drilled points. Yeah. So it is I start with a bundle over the whole graph. Yeah. Right? Yeah. Yeah, so that makes sense. Okay. So then, so all these smaller bundles that I have over the components away from the drilled points, so they are cubulated. So this is my ingredients of the combination theorem. So if my bundle is over, yes, that will always work. Exactly, because then I just have surface groups. Okay. So what is here? So here my components are, on one side I have essentially a fiber 3 manifold component. So this you can just forget about this hanging edge. It can homotop it away. And on the other side you have like a contractible guy. So this is just a surface group. So this is a surface group which is cubulated. This is a 3 manifold group which is also cubulated. And if you start with a hyperbolic bundle and you don't avoid that no homotopy condition, then we prove that the resulting drilled bundle, this guy, has cubulated fundamentally. So that is the simplest instance of our result. So let me know if you have any more questions. Otherwise, I'll start getting into the proof just a little bit. We only have 12 minutes left. Okay. So no more questions, right? Okay. Yeah? Right. So for example, you have the bundle structure, right? So, and you can start with a curve and flow it along the bundle. And come back, for example, in the same fiber, but they're actually homotopic through the entire. Yeah. Exactly. Yeah. No, we haven't proved that these are not cubulated, but a proof won't work. That's it. Right. So even though, well, we are saying that we are actually trying to prove a non-quasi-convex combination theorem, all we have is at our disposal are quasi-convex combination theorems. Right. So I'll just write down the one that we're using. Proof steps. So if you look at that bundle over there, it started off with a hyperbolic bundle, and now you have introduced some torus boundary components, and it might be natural to guess that, okay, now this drilled bundle is actually relatively hyperbolic, little fundamental groups with the torus, the Z2s coming from the torus being the parabolic subgroups. So if you just hang on to that idea, then you can apply this theorem of Weiss, try to apply, which is that if G is a group such that G is hyperbolic relative to virtual abelian subgroups, number 2 is G has a graph of group structure called G gamma with one thing is relatively quasi-convex edge groups. Well, for me, all my edge groups were quasi-convex to begin with, which I'll talk about in some time. all vertex spaces are cubulable. And the fourth thing is sort of a no accidental parabolics condition. So I'll spell it out. For every edge E, GE has no non-trivial intersection with every parabolic that you have, Z2 that you have, in the complement of the edges. So I want to say this is pi1 of gamma minus E, but I can also write this as the graph of groups restricted to the complement of the edge. So if all these conditions hold, then G is cubulable. Gamma is the underlying graph, G gamma. Okay? So this is what you want to use. And, well, we need to be able to use this, first of all, we have to prove that our group is hyperbolic relative to some abelian subgroups. And this is hard. This is where most of the work goes in. This is kind of easy, showing that the vertex groups are cubulable, because the vertex groups will essentially come from the bundles, the restriction of the bundles onto these components that I just described here. So I'll describe this in our example in just a second. This comes from sort of this no homotopy between two sigma I, sigma j that I had. It's also not hard to see, but I probably won't talk about it. It's a topological thing. And number two essentially, given a natural graph of group structures, which is kind of staring at us in that figure over there, given a natural graph of group structures, number two also isn't too hard. It follows from the proof of one, follows along with one. So, right, so that is the sketch of at least, sketch of the proof, assuming that you somehow can prove that G is actually relatively hyperbolic. So I have 5 minutes left. I can, I guess, describe this graph of group structure. The hyperbolicity result is really long, the proof of that. Okay, so I have this space over here. Yeah. So right, so exactly, that's what I'm going to describe. Yeah. So just to simplify the picture a little bit, I'll get rid of this drilling as well. Doesn't really change anything. Save me some work. So I can just ignore this fiber altogether. Okay, so let's give it names. 1 and 2. I said the vertices would be the bundles corresponding to the complements of the drilled points. So these will be my two vertices. They're cubulated as required. Now edge spaces. So what do you do for the edge spaces? So there has to be some edges lying in here, and it's not very apparent right now. But what you do is, okay, let's call this guy M drilled. We'll homotope this drilled three-manifold a little bit to this figure. So note that in the complement of this curve sigma naught, there are two subsurfaces, sigma 1 and sigma 2, and then there is this torus missing in the middle of my surface cross I. So well, I don't really know how to motivate the homotopy very clearly, the visual structure. So the homotopy takes this guy to this guy. So you, on the side you have two copies of your surface, and on the middle you have the subsurface plus I hanging in between. So is this somewhat believable that this is also this is homotopic to my M drill that I had over there? If it's not believable, it's acceptable, but this is really my edge space structure. So this one will be my pi 1 sigma 1. This one will be my pi 1 sigma 2. And right, so this is my graphical group structure, and the only parabolic that you have is lying somewhere over here. This is where the Z2 lies. Z2 coming from this torus. And you can take it as an exercise to check if the fourth condition holds. What's the fourth condition? Yeah, this one holds, because if you remove an edge, since the Z2 lies between two edges, if you remove one edge like I've removed over here, then there's no Z2 remaining in the rest of the graph with any Z2 in the complement. So this holds very easily. This also is done. You have to prove hyperbolicity, and as I said, this relatively quasi-convex edge groups that will follow somewhat from the hyperbolicity proof. But you can also see that you have these subsurfaces as edge spaces, and it's somewhat old result that you have when you have these subsurfaces inside actual undrilled bundles, they are quasi-convex. So it's somewhat believable that you will get this relative quasi-convexity as well. So I think I'll stop here. Don't anymore. Thanks.
Questions for the speaker?
Yes, you push it away. Yes, we push it away to the boundary. So I can draw a better picture. So. Yeah, so there is not a mapping torus. There is a torus over here. So this line that's very badly drawn. Oh, okay. Yeah. So I've left it untouched. So this just becomes one of the vertex spaces. Yeah. Yeah. So, any more questions? Yeah. Yes, exactly. Yeah. Nothing. If the curve is not separating, then this edge space that I've drawn here. So instead of two edge space, you'll just have one edge space, and that will be the subsurface, which is the original surface minus a single curve, which is non-separating. Edge group to vertex group. So here you have just it will just follow the glowing that you have here. So yeah. You have drilled, but in the undrilled bundle, do you have undrilled bundle anywhere? Anyway, so if you just forget about the drilling, here you have this subsurface, and that glues just by the product structure to the three manifold on the side. So that is the glue. Okay, so makes sense. I can tell you more, like later. No. That is the hard work. That is.
No, I mean the first assumption.
Yeah.
Pi 1 of E is hyperbolic.
Oh, that one. Right. So that is right. So we started with some action of. of the free group on the fundamental group of on the surface group. Right, so this action has to have some property. So I don't know these properties very well, but if this action is convex co-compact, then the resulting extension will be hyperbolic. There are better notions, I guess. Yeah. But yeah, I'm not the expert on that area. Yeah.
Thank you.
Yeah.
Okay. Any more questions? Then let's thank the speaker again. And we will meet at 4:50.